Welcome to this video on the work energy theorem, where we'll calculate the work done on a bullet being fired from a gun, the change in energy of the bullet as it's fired, and we'll find the bullet's velocity and acceleration. A 35-gram bullet is fired from a 25-centimeter gun barrel. The bullet experiences a constant force of 4.6 times 10 to the 3 newtons while in the gun barrel. In part A, we'll calculate what is the work done on the bullet by the gun barrel. In part B, the kinetic energy of the bullet as it leaves the gun barrel. In part C, the velocity of the bullet as it leaves the gun barrel. And in part D, the acceleration of the bullet within the gun barrel. Let's start part A by drawing a diagram on the right. The gun barrel is 25 centimeters long. That's 0.25 meters. There's a force of 4,600 newtons acting on the bullet. The mass of the bullet is equal to 35 grams. That's 0.035 kilograms. We're now ready to start solving part A. What is the work done on the bullet by the gun barrel? For this, we'll use our equation work is equal to the force multiplied by the displacement. Substituting our values, the work is equal to the force of 4,600 newtons multiplied by the displacement, which is the length of the barrel in meters, so 0.25 meters. 4,600 multiplied by 0.25 meters gives a work of 1,150 joules, or 1.15 times 10 to the 3 joules. This can also be written as 1.15 kilojoules. We need to determine if the work done on the bullet is positive or negative, so let's examine the direction of our force and our displacement. Our force is towards the right, and so is our displacement. Because the orientation of our force and our displacement is in the same direction, we do positive work. Remember, another way to look at this is using the work energy theorem. Work is equal to the change in energy. The bullet accelerates towards the right from an initial velocity of 0. That means the bullet gains kinetic energy. And if we have a positive energy or an energy gain, we also have positive work. And that supports the answer we found looking at the direction of our force and our displacement. What is the work done on the bullet by the gun barrel? It's 1.15 kilojoules. We've added it to the side here so we can use it in our future calculations. And now we're ready to solve part B. In part B, we're asked to find what is the kinetic energy of the bullet as it leaves the gun barrel. To solve this, we'll use the work energy theorem. Work is equal to the change in energy. When accelerating a bullet in a gun barrel, the type of energy we have is kinetic energy. So we're going to be looking specifically at the change in the kinetic energy. Change in kinetic energy is equal to the kinetic energy final minus the kinetic energy initial that the bullet has. As the bullet has no initial velocity, it also has no initial kinetic energy. So what we're left with is the work is equal to the kinetic energy final of the bullet. So work is equal to the kinetic energy final of the bullet. And we know from part A that the work is equal to 1.15 kilojoules. So what is the kinetic energy of the bullet as it leaves the gun? It's the same as the amount of work the gun does on the bullet, and that's 1.15 kilojoules. We can also add this value to the side for future calculations. So the energy kinetic final of the bullet is equal to 1.15 kilojoules. And now we're ready to solve part C. In part C, we're asked to find the velocity of the bullet as it leaves the gun barrel. Because we just found the kinetic energy of the bullet right before leaving the gun barrel, we can use this to find the velocity of our bullet. So the energy kinetic is equal to 1/2 multiplied by the mass of the bullet multiplied by the velocity squared of the bullet. Substituting our values into the equation for kinetic energy, we have an energy kinetic final of 1.15 kilojoules, so 1,150 joules, and this is equal to 1/2 multiplied by the mass of the bullet in kilograms, which is 35 grams, so 0.035 kilograms, multiplied by what we're looking for, the velocity squared. I'm just going to add a vector sign right now, so I don't forget to give this a direction in the end. 1/2 multiplied by 0.035 kilograms gives 0.0175 kilograms, and this is still multiplied by our velocity squared and equal to our 1,150 joules. To get our value for the velocity squared all alone, we divide both sides by 0.0175 kilograms. So here, 0.0175 kilograms divided by itself equals 1, and we're just left with our term of velocity squared, and this is equal to 1,150 joules divided by 0.0175 kilograms, which gives us 65,714 meters squared per second squared. And we'll just keep some extra values so that we can avoid rounding errors. And finally, to get our value for the velocity, we take the square root on both sides. On this side, our square root and our squared disappear, leaving us with our velocity, and this is equal to the square root of 65,714, which is 256.35 meters per second. And remember, because we took the square root, this could be either positive or negative, because both the solution negative 256.35 squared and positive 256.35 squared equal 65,714. In physics, only one of these solutions is correct, and it depends on the physics of the problem. In this problem, we define the force as positive, and it's going to the right. So our velocity will also be positive or going to the right. So our final velocity is positive 256 meters per second. And let's add this to the side so we can use it in part D. 256.35. We'll keep the unrounded value to avoid rounding errors in future calculations. Meters per second. What is the velocity of the bullet as it leaves the gun barrel? 256.35 meters per second. We're now ready to start part D. In part D, we're asked to find the acceleration of the bullet within the gun barrel. The great part about this question is that we can solve it two different ways, one using forces and one using kinematics. And if the answer comes out the same, that confirms all our previous answers. Let's start by solving this using dynamics. So we can use our equation for force. Force is equal to mass times acceleration to find the acceleration, because the only force we have here is the force applied by the gun pushing the bullet out of the barrel. The force is equal to the mass of the bullet multiplied by the acceleration of the bullet. Our net force in this scenario is just the force applied by the gun on the bullet, accelerating it down the length of the barrel. We have no force of friction in this question, so we have no opposing force to our force applied. So if we plug in our numbers here, our force applied pushing the bullet down the barrel is 4,600 newtons, and this is equal to the mass of our bullet, which is 0.035 kilograms, multiplied by the acceleration of the bullet. Our acceleration is being multiplied by 0.035 kilograms, so to get our acceleration all alone, we have to divide both sides by 0.035 kilograms. On this side, 0.035 kilograms divided by 0.035 kilograms is 1, leaving us with our acceleration. And on this side, 4,600 divided by 0.035 kilograms gives us an acceleration of 1.31 times 10 to the 5 meters per second squared. We can now solve the problem using kinematics, confirming our answer using dynamics. So let's first start by listing our variables before we pick our kinematic equation. So we have the velocity that the bullet leaves the gun at, and this is our velocity final. So our velocity final is equal to 256.35 meters per second. We also have our velocity initial. Our velocity initial was equal to 0 meters per second because the bullet starts at rest. And we have the distance the bullet is accelerated for. So the displacement in this case, d, is equal to 0.25 meters. We're looking for our acceleration. So our acceleration is what we're looking for. It's our question mark. And we don't have the time. We don't know how long the bullet is accelerated for. But luckily, we have 3 knowns and we have our unknowns. So now we can select our equation. We need an equation that doesn't have time in it because we're not looking for time and we don't have time. So this equation here has time. This equation has time. This one doesn't have time. Let's just confirm that yes, this one also has time. So we'll solve for the acceleration using this equation here. Vf squared is equal to Vi squared plus 2 multiplied by the acceleration multiplied by the displacement. Substituting our values into our equation, our Vi is equal to 0. Our Vf is equal to 256.35 meters per second. And this is squared, and this is equal to 2 multiplied by the variable we're looking for, our acceleration, multiplied by our displacement, which is 0.25 meters. 256.35 squared gives 65,715 meters squared per second squared, and we'll keep extra values all the way through this calculation to avoid rounding errors. And this is equal to 2 times 0.25, which is 0.5 meters multiplied by the acceleration. Since our acceleration is multiplied by 0.5 to get our acceleration all alone, we divide both sides by 0.5 meters. So 0.5 meters divided by 0.5 meters is 1, leaving us with our acceleration. And 65,715 divided by 0.5 confirms our answer from before. It's 1.31 times 10 to the 5 meters per second squared. Having these two solutions come out the same should give you a lot of confidence in everything we've done, because our acceleration here from dynamics was calculated using values that were given in the question, our force and the mass of our bullet. And here we calculated the acceleration using kinematics, but remember the velocity was calculated from the kinetic energy, which was calculated by the work done on the bullet. So the fact that both of these accelerations came out at the end, and we took such different routes to calculate them, should give you a lot of confidence in everything we've done in this question from part A to part D. So what is the acceleration of the bullet within the gun barrel? It's 1.31 times 10 to the 5 meters per second squared. Thank you for watching this question on the work energy theorem, where we calculated the work done on a bullet, the change in energy of the bullet as it accelerated down the barrel, the velocity of the bullet as it left the barrel, and the acceleration of the bullet within the barrel.